Okay, so we're going to do 21.9. So this is on the consumer side. So on the question 21.6, we have finished doing for the production side. So this question is going to be about the consumer side. Okay, so we try to find a general equilibrium in which all the firms on the production side are maximizing their profits. And on the consumer side, we are trying to find the conditions for all the consumer to be maximizing their utility. Okay, and after that, we combine the production and the consumption side together in order to obtain the general equilibrium. Okay, so in this question over here, we are going to deal with the consumer, and then after that, we are going to derive the condition in the general equilibrium for both the consumer and the producers in the market. Okay, so we got recharge and save. So these are the two consumers in the market, and each of them are given the utility function. So the U for recharge is equal to BR times CR divided by BR plus CR. Okay, where B and C are just basically the consumption of wood B and C, and the utility for save is BS CS divided by BS plus CS. Okay, so the first part is asking you to write down the expression for save utility, showing that he consumed the share of the output that recharge doesn't. Okay, so it's pretty straightforward. We are already having a utility function for save, which is equal to BS CS divided by BS plus CS. Okay, and so given that okay, BS is basically equal to B minus BR. Okay, so he's going to consume whatever left that recharge doesn't consume. Okay, so the total consumption of B, it has to be equal to the total amount B available in the market. And very similar, CS, it has to be equal to C minus CR. Okay, so if we substitute these into the utility function over here, we will get US is going to be equal to B minus BR times C minus CR, and everything divided by B minus BR plus C minus CR. Okay, so that will give you B minus BR and C minus CR B plus C, okay, minus BR plus CR. Okay, so I just got B minus BR, C minus CR. Now B plus C is given by the production function above, which is equal to K to a power half, L to a power half, everything square. Okay, which is given to you over here. Yep, so we just substitute that into here, and the rest is just going to remain the same. So minus BR plus CR. Okay, so as you can see, the utility function for save is going to be a function of BR and CR, which is the consumption of B and C by recharge. Okay, so whatever recharge consumed over here, the rest is going to go to save, and so therefore that is the reason why the utility for save is a function of BR and CR. Okay. All right, so part B, asking you to show, so assume that set is meeting a utility target of US0. Write out expression for recharge of utility maximization problem. Okay, so the problem for recharge is to basically maximize his utility function. Okay, so he want to maximize his utility function UR, which is equal to BR times CR, everything divided by BR plus CR. Okay, subject to the constraint that set is basically using or achieving a target utility of US0. Okay, so US, which is equal to BS times CS, or we already derived earlier, it's just a function of BR and CR. Okay, so I got so US equal to B minus BR times C minus CR, everything divided by K half L half square minus BR plus CR. Okay, now this has to be equal to a US0, which is the target utility that it's going to achieve. So as you can see, we have a utility function in terms of PR and CR, and our constraint is also going to be a function of BR and CR, which is what we want. Okay, so it just basically the problem where Recharge is trying to find the optimal amount of BR and CR he would like to consume in order for SET to be reaching a level of utility target US0. Okay. All right, so that is the part B. Now part C, asking you to calculate Recharge's marginal utilities MUBR and MUCR and his marginal rate of substitution, and we calculate for SET as well. Okay. Okay, so marginal utility for for Recharge for B is going to be the differential of the utility function for Recharge. Okay, with respect to B. Okay, so if I differentiate this utility function over here with respect to B, now over here I'm going to apply the quotient rule where I got two things on the new. So this is numerator, this is denominator. I'm just using the quotient rule. Okay, so I'm going to get so I differentiate the numerator with respect to BR. I get CR, and times the denominator, which is BR plus CR, minus the numerator remain the same, so BR CR times the differential of the denominator with respect to BR, so that is going to give me 1. Okay, and everything divided by BR plus CR square. Okay, so simplify this. I'll expand the bracket over here. CR times BR minus CR times BR, that will just cancel out. So what I'm left with is just CR square divided by BR plus CR square. So that is CR divided by BR plus CR, everything square. Okay. All right, so very similar for the marginal utility for C, of C for Recharge. That's just the differential of the utility of Recharge with respect to CR. Okay. So I'm going to get a very similar result. I'm using the quotient rule again. I'll get BR plus CR minus BR times CR times 1, and everything divided by BR plus CR square. Okay. So that will give me BR square and everything divided by BR plus CR square. Okay, so that is BR on BR plus CR, everything square. Right, so from here, the marginal rate of substitution for Recharge is just going to be the negative of the ratio of the marginal utility. Okay, so marginal utility of B for Recharge divided by marginal utility of C for Recharge. So if I take these two divided by each other, the denominator will cancel out because they are the same. And so what I'm left with is basically CR square, sorry, negative on BR square. Okay, so that is just negative CR on BR, everything square. All right, so we do very similarly for SET. Now, given that the utility function for SET is exactly the same as the utility function for Recharge, everything is going to be the same. Okay, so therefore, the marginal rate of substitution for SET is just going to be the negative of CS on BS. Okay, so the only thing different is the notation over here, but everything else is the same because it's exactly the same utility function. Okay? Alright, so we have done part C. Now part D asking you to show that if the marginal rate of substitutions are equal, then we got this condition over here. So CR on BR equal to CS on BS equal to C on B. Okay, so if the two marginal rate of substitution for the two consumers are equal to each other, so marginal rate of substitution for recharge is equal to marginal rate of substitution for Seth. Then what we got is CR on BR square equals the negative of CS on BS square. And so therefore the two negative signs cancel out, the square are disappearing. So what I'm left with is CR on BR equal to CS on BS. Okay. So I got the first half of the condition that the question asking you to show. Okay, so now given the fact that CS plus CR is equal to C and BS plus BR is equal to B. Okay, so the total consumption by the two consumers has to be equal to the total amount of goods available in the market. Then what we are having is CR on BR is going to be equal to CS on BS, and CS is just going to be equal to C minus CR. Okay. Now BS is just going to be B minus BR. So from here, if I do cross multiplication, then I get CR times B minus BR is equal to BR C minus CR. Okay, so therefore B CR minus BR CR equal to BR C minus BR CR. Now negative BR CR, negative BR CR cancel out. So what I'm left with is B CR equal to BR C. Okay, so from here you can see that CR on BR is going to be equal to C on B. Okay, so this is the first condition, this is the second condition. Okay, so from the first and the 2 star, we have derived the condition that the question asks you to show, which is CR on BR is equal to CS on BS and equal to C on B. Okay. Now, using the argument previously, confirm that these conditions will be satisfied whenever recharge consumer proportion alpha the output of each good and set consumer proportion of 1 minus alpha. Okay, so if recharge is consuming same proportion alpha of would B and would C, and similarly for Seth, he's going to be consuming the same proportion 1 minus alpha for B and C, then we want to show that this consumption bundles is going to satisfy the Pareto optimal conditions over here, okay, where the two marginal rate of substitutions are equal to each other. Okay, so remember, bear in mind that whenever the marginal rate of substitution for two consumers are equal to each other, the two indifferent curves are tangent to each other, and that is the condition for the Pareto, and the tangency point is the Pareto optimal allocation. Okay, so I would say this is the Pareto optimal allocation condition, because this condition is where the marginal rate of substitutions are equal to each other. Okay. All right, so the question asking you to show that whenever the consumer is consuming the same proportion of B and C, then the consumption bundle is going to be Pareto optimal. Okay, so so if recharge consumes BR CR equal to alpha of B and C, which is alpha B and alpha C. Okay, so the same proportion of B and C, then we know that CR on BR is going to be equal to alpha C on alpha B, and that is just going to be equal to C on B. Okay, so as you can see, this satisfies the condition over here for the Pareto optimal allocation. Okay, so therefore, the consumption bundle alpha B, alpha C is Pareto optimal. Okay, very similar for Seth if he consumes PS, CS equal to 1 minus alpha B and C, okay, which is 1 minus alpha B and 1 minus alpha C. Then we can derive straight away that his marginal rate of substitution or CS on BS is going to be equal to 1 minus alpha C on 1 minus alpha B, and that is just C on B. Okay, so as you can see, it's satisfying the condition over here, and these two marginal rate of substitutions are equal to each other and equal to C on B. Okay, so therefore, this consumption bundle for set is optimal, is Pareto optimal as well. Okay, 1 minus alpha B, 1 minus alpha C, okay, is Pareto optimal. Okay, so part A is asking you to show on a diagram the production possibility frontier and then add an Edgeworth box which has an upper right hand vertex at J dash, and within the box show the Pareto efficient allocations that satisfy the condition obtaining in part D. Okay, so first of all, I will be having a diagram in which I have the production possibility frontier first. So I will have something like this, and I will have something around here is my Pareto my production possibility frontier. Okay, so now on the horizontal I will have B, and on the vertical I will have the product C. So production possibility frontier telling you the optimal combination of B and C an economy can produce given the availability of capital and labor in the economy. Okay, so if I just pick a random point on the PPF side, I'll pick a point over here, which is J dash. So this is going to tell you this is the maximum amount of B, and this is the maximum amount of C that the economy can produce. Okay, so this point J dash on the production possibility frontier is specifying the total amount B and C available in the market. Okay, and so therefore my Edgeworth box is going to just be the box covered by these two B and C amount. Okay, so this is the total availability of the total amount would B and C available in the market. And so on the two origin over here, I will have a two consumer recharge over here on the bottom corner, and Seth over here on the top corner. Okay, so now I want to draw all of the Pareto optimal allocations. Okay, so bear in mind that from part D, okay, all of the Pareto optimal allocations is going to satisfy the conditions where CR on BR is going to be equal to CS on BS and equal to C on B. Okay, so any consumption bundle BRCR or BSCS by recharge and Seth that is satisfying this condition is going to be the Pareto optimal allocation. So now C on B, as you can see over here, Okay, so as we derive from part D, any allocation such that the consumer is consuming a same proportion of B and C is going to be the Pareto optimal allocation. Okay, so if, so for example, Richard want to consume alpha units of B and also alpha units of C, that is going to be the optimal allocation. Okay. So to draw all of those allocations on a diagram, I know that all of those allocations has to be staying on the line with the slope of C on B. Okay, so I got C over here on the vertical, B over here on the horizontal. So if I got a straight line going from this corner to this corner over here, okay, then the slope of this line is going to be C on B. Okay, so any point on this line, okay, is going to result in the ratio of equal to C on B. So basically, this point over here where Richard is consuming a certain amount of C, a certain amount of B, okay, and so this is basically alpha C, okay, and this is basically alpha B. Because how do I know these are the same alpha? Because at this point, the slope is C on B. Okay, so it has to be the vertical divided by the horizontal. Now vertical is this, okay? And horizontal is this. So it has to be alpha C and alpha B divided by each other in order to get C and B. So having said that, I would just want to say that any point along this line is going to be Pareto optimal allocation because it's going to have the ratio of C on B, okay? And so therefore, any allocations on this, so this is the Pareto efficient or Pareto optimal okay, allocations. All right, so part F asking you to show that to calculate a common marginal rate substitution for all the allocation in the Pareto set, and asking you to draw an indifferent curve for each as and set, assuming that alpha equal to a half. Okay, so each of the consumer is consuming half of the output of the goods. Okay. Okay, so what is the marginal rate of substitution for each of the consumer at this optimal allocation point? Okay, so part F. So we know at of the Pareto, okay, efficient, okay, allocation points, then CR on BR is equal to CS on BS equal to C on B. I just have to keep repeating this, okay? Now, the marginal rate of substitution for recharge is, as we found before, equal to a negative of CR on BR square, okay? And so in this case, it's just going to be equal to negative C on B square, and very similar for set is equal to CS on BS, everything square, and so therefore it's just equal to C on B square. And as you can see, these two marginal rate substitutions are equal to each other, okay? And so therefore, that is the reason why we have Pareto efficient allocations. Okay, now if alpha equal to a half, okay, which is basically mean that recharge is consuming CR and BR equal to a half of C and a half of B. Okay, and very similar for set, he is going to be consuming half of each of the goods, so half of C and half of B. Okay, so we want to show this optimal allocation on the diagram. Okay, so that is just going to be, so I would have half the B over here, so half of B is somewhere, I'll say somewhere here. Okay, so this is half of B. And so C over here, so this is going to be half of C. Okay, so this is the allocation. Okay, so where actually the consumer is consuming half of the total amount of goods available in the market. So we want to draw the two indifferent curves corresponding to this Pareto optimal allocation. All right, so when you draw, you just have to make sure that the two indifferent curves are tangent to each other, okay? Because so we know that so the marginal rate of substitution for recharge over here, which is the slope of the indifferent curve, okay, equal to negative C CR on BR square, okay, which is half of C and half of B, everything squared, so that equal to negative C on B squared. Okay, and very similar for marginal rate of substitution for Z equal to negative C on B as well. Okay, so the two indifferent curves are going to be tangent to each other at this point. So what you want to draw is to draw the two indifferent curves that is going through the same point. So this is indifferent curve for recharge, and this is going to be the indifferent curve for Z. Okay, and the two indifferent curves are tangent to each other at this point over here. And that is the Pareto optimal allocation in which the two consumers each consuming half of the goods. Okay, now explain why the allocation of goods in the box is not consistent with the general equilibrium. Okay, so now what is the conditions for the general equilibrium to exist? So the general equilibrium is where all of the consumers are maximizing their utility functions, okay? So, so where the marginal rate of substitution for recharge is equal to the marginal rate of substitution for Z, okay? So that is the Pareto optimal allocations for the consumer side. And for the production side, it has to be the case that all the firms are maximizing their profits, okay, from producing, and so it has to be the case that okay, it's equal to the price of B on the price of C. Okay, so that is for the consumer side where okay, where the consumers are trying to be maximizing their utility. Okay, so and on the producer side, the firm will try to maximize the firm's profit, okay, by producing such that the marginal rate of transformation has to be equal to the price ratio. So now marginal rate of transformation is just basically the slope of the production possibility frontier, okay? So the firm is going to be producing somewhat such that the combination of B and C such that the marginal rate of transformation, which is the slope of the production possibility frontier, okay, it has to be equal to the price ratio B and PC. Okay, so now from okay, so from exercise X 21.6 that we did earlier, we have found that PB is equal to PC equal to I think WK times WL divided by WK plus WL or something like this. Okay, so we know that the price of these tools are the same. Okay, so therefore the condition is the marginal rate of transformation is going to be negative, equal to -1. Okay, it's where PB equal to PC. Now, as you can see, in order for the general equilibrium to exist, then the marginal rate of substitution for the consumer, it has to be equal to the negative of the price ratio, which is equal to -1 as well. Okay, so for the general equilibrium to exist, then marginal rate of substitution for R has to be equal to marginal rate of substitution for S, and equal to marginal rate of transformation equal to -1. Okay, so we know that marginal rate of substitution for these two consumers are equal to -C on B squared, and it has to be equal to -1. Okay, so negative sign cancel out, then C on B squared has to be equal to 1, so C on B has to be equal to 1, so C will have to be equal to B. All right, so unless C is equal to B, then we do not have the general equilibrium. Okay, so if any applications for any productions where C is different from B, then the general equilibrium is does not exist. Okay. So that is basically explaining part G as well, which is asking you to show that the condition where the marginal rate of substitution equal to each other, equal to marginal rate of transformation, equal to the negative price ratio. Okay, can only be satisfied when B equal to C, which is what we showed earlier. Okay, so B has to be equal to C in order for these things to be equal to each other, equal to -1. Okay, so it's asking you to sketch a new diagram showing the production possibility frontier in which B equal to C. Okay, and the associated Edgeworth box again with the Pareto set. And the equilibrium where alpha equal to a quarter and alpha equal to a 3/4. Okay, now it's pretty straightforward. Again, we just have to we just have to have a diagram again where I got B, C on a vertical, B on a horizontal, and I got the production possibility frontier again here. Okay, now I would have to pick a production point on the PPF such that B is equal to C. Okay, so that is going to be just the middle point over here. Okay, so at this middle point of production, I would have the box such that, so this is the amount of C, this is the amount of B, this is 0. Okay, so B is going to be equal to C in this case. Okay, so this is the point H dash. So my Edgeworth box is going to be just again represented by this. Okay. Okay, and this box is basically a square, okay, where the value of B is equal to the value of C. Okay, and again, I just have okay, so a straight line that is going to connect from here to here, just like what I did before. Okay, so on this corner I will have recharge, and this corner I will have set. Okay, so this line over here is just basically having the slope of C on B. Okay, so in this case it's just equal to 1. So any point on this line is going to have a ratio C on B equal to 1. Okay, now we want alpha to be a quarter. So the first case is where alpha equal to a quarter, which is basically means that recharge is consuming a quarter of both B and C. Okay, so B are CR is equal to a quarter of B and a quarter of C. So that, so I got B over here, so this is half of B, so a quarter will be somewhere here. So that's a quarter of B. And I know the consumption point, it has to be on this line in order for Richard to be consuming the same fraction of C. So this is a quarter of C. Okay, so at this point, we want to show the two indifferent curves tangent to each other and having the slope of -1, okay, which is the case over here, where this is the Warasian equilibrium or the general equilibrium. Okay, so if I draw a line that's going from this point to this point over here, okay, then you know that this line is going to have a slope of -C on B, and that is just -1, okay, because C is equal to B. Okay, so I want to draw a line that is going through this point over here, okay, and it's parallel to the line with the slope of -1, because what I want to do is okay, so this line will have the slope of -1. And so if I draw the two indifferent curve like this, okay, so this is the indifferent curve for recharge, and this is the indifferent curve for self, and they are tangent at this point with the slope of -1. And so therefore we are achieving the general equilibrium condition. Okay, so this is the Warasian equilibrium. And so very similar for the second case where alpha equal to 3/3 is going to be exactly the same, where BR, CR, so recharge is going to be consuming 3/3 of B and 3/3 of C. So that is just going to be somewhere here, so 3/3 of B. And so if you are going all the way up to the line, over here you will get, so this point is 3/3 of C. So this is the consumption point, okay? And this is again just another Warasian equilibrium or the Pareto optimal allocation, okay? So again, if I draw the two indifferent curves that are tangent to each other and also tangent to the line with the slope of -1 that is going through this, okay? And if I draw the two indifferent curves like this. Okay, so they are tangent to each other and they are tangent to the line with the slope of -1. Okay, then again, so this, sorry, I should make tangent, not cutting through the line. So you want to like this. Okay, so this is my indifferent curve for set, indifferent curve for recharge. They're cutting at this point. So this is another equilibrium if the consumer is consuming 3. So if recharge is consuming 3/3 of the products. Okay.